EDX Decision 1, Algorithms, Sorting, Packing and Other Algorithms. Sorting algorithms using the bubble sort algorithm. We may need to sort a list of numbers into ascending order or descending order, or a list of words or letters into alphabetical order, and it's important we check the order required in the question before we start. We might do this because we need a sorted list to perform some other algorithm, for example the first fit decreasing algorithm. In this specification we will cover the two following algorithms, the bubble sort algorithm and the quick sort algorithm. The bubble sort algorithm. Step 1. If there is only one number in the current list, then stop. Step 2. Make one pass down the current list, starting at the beginning of the list, comparing numbers in pairs and swapping as necessary. Step 3. If no swaps have occurred, then stop. Otherwise, reduce the length of the current list by leaving out the last element of the current list and return to step 1. At the beginning, the current list is the whole list to be sorted. This algorithm will make a lot more sense when you see it in practice. It's called the bubble sort algorithm because when we are sorting numbers into ascending order, you'll see the bigger, heavier numbers sink quickly to the bottom and the smaller, lighter ones slowly float to the top. So in this first example, we're going to sort 5, 8, 3, 12, 1, 15, 7 and 6 into ascending order. So we want the smallest number at the beginning and the biggest number at the end. And I'm going to show you in some detail the first pass through this process. So the first thing we do, the algorithm says, is take the current list, which is all the numbers, and start at the beginning, comparing numbers in pairs and swap where necessary. So we compare with 5 with 8 and we don't need to swap. Then we compare 8 with 3. 8 is bigger than 3, so therefore we would swap the 8 with the 3. So at the current we've got 5, 3 and 8. Now we compare 8 with 12. We don't need to swap. Then we compare 12 with 1 and we would need to swap because 1 is smaller than 12. So there's a swap. Now we compare 12 with 15 and we don't need to swap. Then we compare 15 with 7 and we would need to swap. And finally we compare 15 with 6 and we would need to swap there. So that's what the first pass through the numbers would achieve. And it's worth taking note here, we'll be looking at this in a bit more detail in a moment. The number of comparisons, how many comparisons did we make? We made 1, 2, 3, 4, 5, 6, 7 comparisons of numbers. And how many times did we swap two numbers? There was 1 swap, 2 swaps, 3 swaps, 4 swaps. So in that first pass we made 7 comparisons and 4 swaps. So that's the first pass completed. 7 comparisons and 4 swaps. So I'm going to do the next pass now, and I'm going to indicate a comparison with a line, and if I make a swap I'll put an arrow on the end. It's interesting to look at that first pass. After that first pass, 15 has sunk to the bottom and I've put it in red. If I was doing a question I might just circle it so I know that 15 is in the right place. If you remember, the algorithm says looking at the current list. So this is my current list now. I've got 7 numbers. Okay, I'm going to do the whole pass in one line, which is highly recommended by the examiners. So this is what the second pass would look like. Compare 5 with 3 and I would need to swap them. So that would put 3 there. So I've got 5 in this position. Compare 5 with 8. Would not need swapping, so 5 would stay in the second place. compare 8 with 1 would need to be swapped. So that's 1, and this number here is 8. Compare 8 with 12. Comparing 8 with 12 doesn't need to be swapped. Compare 12 with 7. They would need to be swapped. So 12 is in this position now. Comparing 12 with 6, that would need to be swapped. So we get 6 there, 12, and we know that 15 was already in the right place, so we don't compare with that. So we've now 12 has sunk to its correct position near the bottom of the list, and we made, if you count the comparisons, we made 6 comparisons, and where the arrows are was a swap. So that's 1, 2, 3, 4 swaps were needed. So we now repeat the process from looking at the numbers from 3 to 6. Compare 3 with 5, don't need to swap. Compare 5 with 1, we need to swap, so there's the 1. Comparing 5 with 8, 5 stays where it is. Comparing 8 with 7, we would need to swap. 8's in this position now, so comparing 8 with 6 would also swap. And we know that 12 and 15 were already correct. So 8 has sunk to the bottom, so that one's fixed. We made 5 comparisons, and we made 1, 2, 3 swaps. So this is pass number 4 now. Compare 3 with 1, we'll need to swap. Comparing 3 with 5, don't swap, 3 will stay there. Comparing 5 with 7, don't need to swap. Comparing 7 with 6, we'd need to swap, so 6 has swapped with 7. 8, 12, 15. So these 3 were already fixed in the right place. 7 is now fixed in the right place, and that was 4 comparisons and 2 swaps. One of the most common mistakes now is to think that we can stop because we can see the numbers are in the right order. It's so important that we stop when the algorithm tells us to stop, and the algorithm tells us to stop when there are no more swaps during a pass. So we must keep going now to check. Comparing 1 with 3, we don't need to swap. Comparing 3 with 5, we don't need to swap. Comparing 5 with 6, we don't need to swap. And that's the point where we can terminate the algorithm. We've just done pass number 5 and there were no swaps. We made 3 comparisons and none of them were swaps, and that's when you know you can stop. So we've now fixed all of these numbers at the end of pass number 5. In this example, we're going to do a bubble sort algorithm, but we want to end up in descending order. So we want the biggest number at the beginning and the smallest ones at the end. So we need to do this one extra carefully. So biggest at the beginning, smallest one at the end. So 9 is bigger than 4 when we compare them. So 9 stays where it is. 5 is bigger than 1. So 5 stays where it is. 1 is smaller than 14, so we need to swap. 1 is smaller than 8, so that would swap. 1 is smaller than 2, so that would swap. 1 in that position would be smaller than 11, so there's another swap. And 1 would swap with 10. So 1 would end up there, so that one is fixed. So that was 7 comparisons, and we can count up the swaps as 5 swaps. So now we repeat the process. Remember, if the number's bigger in the comparison, it stays where it is. So 9 is bigger than 5, stays where it is. 5 is smaller than 14, so we need to swap. 5, so that was a swap. 5 would be smaller than 8, so that would swap. 5 is bigger than 2, so 5 stays where it is. 2 is smaller than 11, so that would swap. So now 2 would be smaller than 10, so that would need to swap, and we would have 2 in the correct position. So that was 6 comparisons, and counting up the swaps, 4 swaps. So repeating it again now. Comparing 9 with 14, 9 is smaller, so we would swap. Comparing 9 with 8, 9 is bigger, stays where it is. Comparing 8 with 5, 8 is bigger, stays where it is. Comparing 5 with 11, 5 is smaller, so would swap. Comparing 5 with 10, 5 is smaller, so there'd be a swap. And we now have 5 in the right place. So that was 5 comparisons, 3 swaps. So repeating it again now. Comparing 14 with 9, 14 is bigger, stays where it is. 9 is bigger than 8, stays where it is. 8 is smaller than 11, so would swap. 8 is smaller than 10, so would swap. We've now got 8 in the right place. So that was 4 comparisons and 2 swaps. So carrying on. 14 is bigger than 9, stays where it is. 9 is smaller than 11, so swaps. 9 is smaller than 10, so swaps. We now have 9 in the right place. So it's about keeping things neat and organised as we're going along. So that's 3 comparisons, and we made 2 swaps. So comparing 14 with 11, no need to swap. Comparing 11 with 10, no need to swap. And the algorithm says stop when there are no swaps in a pass. So that means at the end of that pass, we can now stop. We made 2 comparisons and neither of them were swaps, and that's when we know we can stop. So we have all the numbers in descending order. So a quick summary of the bubble sort. The next largest, or smallest, depending with the order you're going for, the next largest number bubbles to the end of the list after each pass. The list gets shorter by 1 element after each pass. The algorithm ends when a complete pass has been made with no swaps. So what did we notice about the number of comparisons after each pass? What I'm hoping you noticed, and you can go back and check, is that the number of comparisons will always reduce by 1 at the end of each pass. What's the maximum number of passes needed for a list of size n? Well, if the list was in completely reverse order from that required, you would require n minus 1 passes in order to get it back into the order requested. Note that there are many videos on Integral and YouTube, so make sure you choose the videos carefully to match the algorithm that we have studied. In the next session, we'll be looking at sorting algorithms and the quick sort algorithm.